Good morning, everyone. This is Ben Keyser with Applied Flow Technology. I want to thank you all for joining me this morning on this lovely, fine Wednesday. And today we're going to be talking about eliminating wasted energy and increasing cost savings. And it's going to bring me to a question I want to ask you all. But before we get into that, I want to let you all know that this webinar is being recorded. And so shortly after the recording, later this week, you'll be sent a link with that way you can watch the recording at your own time. You'll be able to forward it on to your colleagues. And then the webinar will also exist in our webinar library. If you're not familiar with how to find our webinar library, you just go to AFT.com, and then under the Learning Center, go to Webinars and then Webinar Library. Here you would fill out the brief information on the form there and click on Submit, and then you'll be able to access various product webinars. And so the webinar that I'll be doing today will end up in the Fathom webinar library. So that's where you can find the content. Okay, so the question I want to ask is, did you know that pumping systems account for about 25% of the electrical motor energy consumption, as well as 20 to 60% of total electrical energy usage in various industrial systems? The thing is, these pumping systems that are operating are not operating very efficiently for the most part. The system gets designed, it's turned on, and then immediately you throttle the valve to control to the flow rate that you want. And that's just like driving your car with the foot on the brake pad as well as the gas. It's going to tear up your car. Well, same thing here. If you're throttling that flow, that's going to cause the pump to operate away from its sweet spot. And not only are you wasting energy, but you're also going to cause a lot of other problems, vibrational issues. It's going to increase your seal failure rate and lots of things that you want to try and avoid. So we're going to talk about all that stuff today. Basically, you don't want to be just pumping, money right out of the pipeline there. You want to try to find ways to increase your cost savings as well as eliminate those expensive repair costs. Here's what we're talking about today. Going to go over a look into potential areas where you can find some electrical energy cost savings. We're going to take a look into understanding the pump impacts on high energy costs. Spoiler alert, nobody cares about energy costs. And it's very surprising to me. And the people, the EPC companies don't care. And the people that should care, being the owner operators, they don't care. And we'll see some reasons why. And so the key thing is, if no one cares about energy costs, what should we focus on? So we'll dip into that. I'm going to go into some concepts to think about for developing better system designs. We'll look at a few case studies, and then I'll show a couple of things here in Fathom, a few examples on how you can actually use Fathom to calculate your cost differences on what it would be to use a variable speed drive versus a control valve. And so you'll be able to quantify those exact energy cost savings very, very quickly. Another thing I'll show is not directly related to energy costs, but operational problems. And this will help illustrate why it's really important to get a good flow model of your system, because if you have one, it'll help you determine operational problems that are seen in unintuitive places or are only seen at certain times. And so I'm going to use the goal seeking control and extended time simulation modules to illustrate that. Makes it very easy. And then last but not least, I'll be going over some pump and system interaction details and talking a lot about that. That's establishing pump and system curves. Very easy to generate a pump and system curve in Fathom. I'll show you how to do that. Today, I'm going to be slightly different than my usual webinars in that I have a little bit more to show you in the slides themselves. And when I get to talking about the stuff on pump and system curves, you'll definitely want to focus up and pay attention to that portion. That's a lot more slides, but they're interactive slides, and it'll really help clear a lot of things up. And so let's go ahead and jump in. So here's a breakdown of the potential electric savings that you can find. This is a report that the U.S. Industrial Motor Systems, the U.S. Department of Energy did several years ago. And I've borrowed this slide from the Hydraulic Institute. As you can see, it breaks down the electrical energy savings potential by industry. So these are the different industries, and these are different categories of areas where you can experience some energy savings. So as you can see here, based upon the blue curves right here, in every single industrial system here, the pump and system is going to give you the best areas for saving electrical energy and getting some really good cost savings in there. So that's where you're going to get your best savings. The next area would be compressed air systems. That's the pink line. Upgrading your motors, that can sometimes help you save some energy, but not as much as just looking at the pump system itself. Maybe downsizing the motor, that could maybe help you save some energy. Replacing or rewinding your motors, modifying your fan system, and then evaluating other systems. So fundamentally, the area where you're going to experience the biggest amount of savings is in the pump system itself, and we're going to learn why that is. And so this is a technical report that a Finnish company did several years ago, and you can find it's the Expert Systems for a Diagnosis of the Condition and Performance of Centrifugal Pumps. What they did is they evaluated just about 1,700 pumps across 20 different process plants. Here's what they found. On average, the pumping efficiency for those pumping systems were below 40%. So very, very inefficient operation there. Another issue is that they found that over 10% of those pumps were even running below 10% efficiency. So again, just throwing money right out the window. Key factors that affect your pump efficiency would be throttle valves in your system. The other issue is pumps that are way oversized. Here's the problem of these systems that have been designed over the last, couple hundred of years is an engineer goes through the process where they are designing their system, they throw a safety factor on it. They give it to their manager. The manager looks over the project. The manager throws their safety factor on the project. Once the project gets approved, it puts another safety factor on, and then when they go to the pump manufacturer to get the pump manufacturer puts their own safety. So you just have safety factor upon safety factor, and you end up with a pump that's way oversized. It gives you way, way much higher of a flow than what you need, and you end up throttling your valves in order to get the flow rates that are desired. And that just causes the pump to operate way far away from its best efficiency point. It can cause a lot of issues and wastes a lot of energy. And another problem is that a lot of times seals will wear out. Well, people will go to the seal manufacturer and complain about the seals always having to be replaced. Well, here's the problem. The way that the operator is running the pump, that killed the seal. And so if you operate your pump more efficiently and better, you're going to avoid those problems. So what's the impact of this on life cycle costs? Here's an example for a conventional 75 horsepower pumping system, and we're looking at what the makeup of all the costs are over the 20-year life cycle of that system. And so the total 20-year life cycle cost is $760,000. Okay, well, what makes up that $760,000 over 20 years? 9% is the initial cost, $70,000. That's how much it costs to buy the system, and then you have to install it. Installation is about 8% typically. Well, what does it cost to maintain it? That's a lot higher, 28%. So that includes repair costs. You know, when your equipment fails and you have to replace it and maintain it. Last but not least, your operating costs make up the highest percentage of the total cost of the system. So 55% of the cost, $415,000, is in the operating costs themselves. And what you're going to find, especially if you were to do some creative modeling with Fathom, it's very quick and easy to see how you can dramatically improve the cost savings of these systems. So your operating costs and maintenance costs, they make up 83% of your total costs. Well, here's the problem. You know, what do owner-operator companies and EPC companies care about the most? Initial cost, installation cost. That's all they care about. And that's a major problem because you're trying to purchase the system and get it online as cheap as possible, and then that just jacks up your operating costs and your repair costs. And so things can definitely be done a lot better. Well, if your operating costs and maintenance costs are accounting for 80% of a system's total lifecycle costs, why do owner-operators and EPC companies care so much about installation and initial costs? Well, here are some reasons why. One is simply just, you know, lack of education on piping system operation as a whole. If you go back to your fundamental fluid mechanic classes in college, you know, they don't really address the whole piping system as a whole. Chances are, if you worked on a piping project in your fluid mechanic classes, it only dealt with a very, very small system, you know, one pipe, maybe a few pipes here and there. And you don't learn about how the whole system has interactions with itself, and that's going to be a major impact of what makes up your operating and maintenance costs. Another reason is simply budget constraints. You know, it would be helpful to pay a little bit more money up front by purchasing larger diameter pipes. That way you don't have to get as large of pumps. So initially your costs would be a little bit higher, and you'd be able to see that you would save tons of money over the long run. But the budget prevents that. It doesn't matter. You've got to keep those costs as low as possible. The other issue is that the EPC companies are not stuck with the energy bill. And so when the EPC company is designing the piping system, they don't care about the energy costs either because they're not stuck with it. Finally, here's one of the more important reasons is that there are not many standards that exist that will guide piping system design. Okay, there are certainly, you know, pipe stress standards, and there's, you know, the B31 ASME codes for piping and how to design piping. But the problem is they do not address and provide guidance on the system as a whole. They focus on, you know, smaller pieces of it. And so because of that, EPC companies and owner operators are free to choose if they do a flow analysis and calculate system hydraulics or not. And so they have the ability to not even do pipe flow analysis because why would you do that? Well, you'd have to pay the companies to do it for you. And for those that do choose to do the flow analysis, they can choose how they calculate it. So, you know, rather than doing a good detailed analysis, they may just be doing back of the envelope hand calculations or rules of thumb methods or Excel spreadsheets. And so there's not any standards in place that really guide a good analysis. And if this was in place, where it would force owner operators and EPC companies to, take a better look at their designs, then the systems would run and operate a lot more efficiently and avoid a lot more problems. So if energy costs are not important, quote unquote, then what is? Well, let's look beyond the energy savings itself. Let's forget about energy savings. What are other important factors that would cause us to want to do an analysis of the whole system itself? Improved safety, higher reliability, increased productivity. So if you do a good analysis of the system, you can find ways to increase production levels. Less equipment wear and tear. That's definitely an important one. Reducing maintenance costs, reduced production losses. That's a key issue. If you're running your system at way too high of pressures, maybe you've got leaks happening throughout your network, and that's production losses. You can increase the capacity utilization you already have. And so, as I mentioned, a lot of these systems were way oversized. Well, if you did a good flow analysis to learn how to operate the system more efficiently, then you'd be able to utilize what your system could already do without maybe having to make any system modifications. Reduced environmental impact. What does this all lead to? Better profitability. And so it's all about the money. So obviously it's important to focus on how much energy and cost savings that you can generate. But the other reason is all of these things will help you make more money in the long run. And why focus on pumping systems? The reason is because the pump efficiency is highly influenced by the system it is supplying. Okay, a lot of times people you'll read entries in magazines to increase your pumping efficiency, increase the pumping efficiency. When they give guidance to improve pumping efficiency, what are they talking about? They're usually just saying stick a VFD or a VSD on your pump and that will solve all your problems. No, it won't. The thing is, if you put a variable speed drive on a pump or a variable frequency drive, that can help. That way your pump is not just constantly operating at 100% speed no matter what. It can adjust better to the operating conditions. But the major issue is you have to look at the system itself. Do you have a lot of valves in your system? Are they throttled? Do you have a lot of flow paths that are turned on which may not need to be on? Maybe you're running too many pumps at a time. Maybe you're running 5 pumps when you only need to run 2. Okay, and so it's not just about focusing on the efficiency of the pump itself by putting a VSD on there. It's about focusing on the system as a whole, and that's why doing flow analysis is really helpful because it gives you a much better picture of what's going on in the whole system. All right, erase my pretty drawings again here. So here are some system design concepts that are important to keep in mind, whether you're dealing with a brand new design that you're working on, or if you're dealing with a system that already exists, maybe you're doing an expansion or a retrofit. So here's some concepts to keep in mind. One is if you're designing a single component, you can design that component very, very well. However, that means that your component's only going to be designed for specific conditions. So if you're not accounting for other ways that that component can operate, then it's going to cause issues. It's going to cause those drops in efficiency. It doesn't account for any impacts on the system itself. So designing just a single component is really not your stopping point. You want to go further than that. The next thing is when you design a complete system and you do a good analysis and you design your system and then you run an analysis software like AFT Fathom to check and see, is your design going to work? Well, the advantage here is you can account for component interactions. When you've got pumps operating and heat exchangers having their losses being defined on resistance curves, control valves changing their operation in order to meet their set points. Some funky stuff can happen, and if you do an analysis, you can see all that interacting together. This will also reveal potential problems in unintuitive places. I'm going to show you an example of that later. It allows you to optimize the system. When people talk about optimizing the system, what are they talking about? They're typically only considering optimizing the pump performance. And that's another problem. It's not just about the pump. It's about the piping system itself that's connected to that pump. Okay, so again, when I mentioned earlier that if you were to spend a little bit more money up front and get larger diameter pipes throughout your system, then you wouldn't have to get such a large pump, and you could save tons of money in the long run on those operating costs. Well, again, with those fixed budget constraints, then you're going to run into an issue where you can't spend more than the initial budget. I want to take a quick sidestep and talk about another tool that we offer. If you go to AFT.com, under the products menu, you can find our AFT software overview. These tools right down here, AFT Mercury and AFT Titan, those are very powerful tools. They're basically old versions of Fathom and Arrow on very strong performance enhancers. And what they will do is they will automatically size pipes in your system in order to minimize your life cycle costs or minimize your energy usage or your piping weight. So when you're working with Mercury or Titan, you can have a lot more flexibility to allow those tools to change the pipe sizes throughout your network in different combinations in order to give you the best savings. Well, again, you still might run into a situation where it's wanting to have you purchase more up front, and that's an issue. Well, what you could do is a optimization study with a initial budget constraint. And so that's where your system design has to fit the budget, but still change those pipe sizes and make them a little bit larger. That way you can still save a lot of those energy costs. What we're doing right now is we're taking the capabilities of AFT Mercury that have been around for over 15 years. We're expanding them and improving them. We're integrating them directly into AFT Fathom and AFT Arrow as brand new add-on modules. So if I went into Fathom right here and clicked on the button to turn on the add-on modules, soon you're going to see this option right here to do automated network sizing. That's what the new ANS module will do. It's based off the strong technology that's been around for a long time from Mercury. Excuse me. My throat was going dry there, so I had to rehydrate myself really quick. Again, if none of you have been able to visit us here in Colorado Springs, my advice is make sure that you drink tons and tons of water. It's high altitude and very dry out here, and it's just always best to stay hydrated anyway. Okay, if you approach the system as a whole, you can really get a good look at what's going on around you doing one piece at a time. If you're designing a new system, you can improve the efficiency of your system from the get-go, save money without doing any real-world testing. So that's a major advantage there. You can incorporate potential future modifications, process changes, expansions, and analysis will help you figure out the impact of what's going to happen in those cases. If you're modeling existing systems, you can eliminate cavitation, remove bottlenecks, minimize maintenance and repair costs, increase mean time between failures, maximize uptime and profitability, and improve efficiencies. So if you're looking at the whole system, you can be able to uncover all of these different benefits right here. Okay. So a few case studies that I want to go over. This is a case study that was done for the Chrysler plant in Michigan, in the United States here, and they built a Fathom model of their piping system. It was for their cooling water system here, and as you can see, it's a very, very simple model. Here's all their pumps that were operating, and what they did was they lumped their entire system into this general component right here with a resistance curve. So they were able to model the whole guts of their system in that little teeny piece. And ultimately, what they found is they were able to save $194,000 a year in energy costs, and they won a $200,000 rebate from their local energy utility. So again, you don't have to do a huge rocket science type of analysis in order to get some powerful savings here. Another thing is if you look at the calculations, they match their field measurements very well. And so even keeping it as a simple model, you're going to be able to find ways to dramatically improve your system operation very easily. And here's where you can read about that case study right off of our website. I'm not going to open that there. Another case study was done by a company, TME Engineering, and they worked on a system for the University of Alabama. So for the University of Alabama, this is their entire cooling water, hot water, their district cooling system. And so this is just one of the sections of their pump configurations that you can see. And what they had found was they were able to save $60,000 a year. Well, how do they do that? You've got this ginormous system right here. This is about probably 1,500 pipes and junctions. How are you going to be able to figure out your better operation, for that matter, and energy costs by hand? You can't. So if you do a model, it'll make it a lot more obvious. So what they found when they were modeling their system is one of their buildings right here was taking out a much higher than necessary pressure loss. And so it was starving the whole rest of the system. And so what they recommended was to incorporate a booster pump for that building. That allowed all the rest of the buildings to operate a lot more efficiently. Again, saving $60,000 a year. But again, don't just pay attention to the energy costs that they're saving there. In addition to saving the energy costs, they've prevented equipment failures and prevented expensive repair costs. That's really what you're doing, is by allowing your pumps to operate more efficiently. Here's another system that I want to talk about. It was a raw injection of a brine system that Flowserve was working on. If you go to the Learning Center under Case Studies, you can find this case study right in here. If you did Fathom and then ground injection right here, I want to show you what their system looks like. So what they experienced was over a 5-year time frame, they had 41 repairs costing over $1.2 million. And their mean time between failures was just under 15 months. So they're constantly having problems in their system, having to go back and make repairs, and just had tons and tons of issues. Well, as Flowserve began to look deeper into what was going on, they built a model of their piping network, and this is what the model looks like right here. And so they had 10 pumps in the system. These were vertical supply pumps, and then they had some horizontal booster pumps elsewhere throughout the system. As Flowserve began their analysis, they ran some test cases. They made very good usage of the scenario manager right here, where they model all their individual cases like this. And what they found was the pumps that were operating very far away from their best efficiency point. Look at that. For cases 2 and 3, they had pumps that were operating at as low as 23% of their best efficiency point. So flow being choked back way, way low. Well, here is the problem. Essentially, these 5 pumps when several of them were operating together at the same time, usually they had 3 operating at the same time, they would fight each other. And so when they fight each other, they struggle to find their own operating point on their pump curves. And eventually, you have pumps that are just supplying way, way, way less flow than what they need to actually be supplying. Well, when Flowserve kept going along with this study, they started by turning off various pumps and only running maybe 2 pumps at a time. And when they run only 2 pumps at a time, they would also close off some of these cross-tie valves to eliminate some of that resistance. What they found was they were able to get some dramatic increases in their flow. And so rather than having 3 pumps running, they only ran 2 pumps and they got additional flow. And it was much closer to the flow that they actually needed. In their final case, what they found was by operating these 2 pumps under various conditions right here at a time, their flow rates were able to match a lot closer to their best efficiency point flow rate. So they went from essentially, as low as 23% up to about 75% of the best efficiency point. We're going to talk a lot more about that here in the next few, for the rest of the webinar. So you can read more about that case study there, and these are just the highlights. They found ways to operate their pumps a lot better by simply closing off pumps that were not needed. Again, you're not going to have to do huge magical modifications to your system in order to get it to operate better or to be more efficient. It's simply a matter of maybe turning off a few pumps and motors that don't need to be operating, and it'll, dramatically increase your energy savings and avoid your operational problems. So now that their pumps are operating at 75% efficient, best efficiency point, they're not going to have this problem very much anymore. It's going to dramatically reduce those costs, increase the profitability of their system. I want to mention that I made my presentation available to you in the handout section for the webinar. And so you'll have these links to go read about these case studies. If you're listening into the recorded version and you weren't here live and you want to get a copy of my presentation, email me directly at benkeiser@aft.com and I'll be happy to send it to you. I'll get you my email address at the end of the presentation. Again, it's benkeiser@aft.com. Okay, so let me show you a quick Fathom example. Let me open up this system here real quick. Browse to my location. There we go. All right, so here's what I've done. I have 2 identical systems on the same workspace right here, and I want to go over what's going on. On the system on the left-hand side, I have flow control valves that are controlling to a set point while the pumps are operating at 100% speed. The system on the right-hand side is the same system, but what I've done was I failed these control valves open and they have no loss. It's like they're not even there. The reason why is because I'm going to operate the pumps in this case on variable speed drives. So rather than controlling to a set point with my control valves, the pumps are going to control to a set point. And we're going to evaluate exactly what the cost savings are. Now, I have 2 scenarios. I've got a base scenario and then I have an off-peak scenario. My base scenario is normal operating conditions of a total system flow rate of 3,000 gallons per minute. Okay, so I need 1,500 here and 1,500 here. That means each pump is going to be delivering right around 1,000 GPM. Same idea, but instead I've specified 1,000 gallons per minute, 1,000 gallons per minute, and 1,000 gallons per minute. My peak hour base scenario operation is 4,380 hours. That's basically 12 hours a day, 365 days a year. I'm not going to run this scenario because the system and the pumps were designed to meet the peak hour flow rates, okay? And so the energy costs by using VSDs versus control valves, fairly small. You'll see exactly what those costs are here in a minute. So I'm going to focus on the off-peak hour scenario. So here's what I did. I've got, in my off-peak scenario, it's 1,000 gallons per minute through each heat exchanger. So instead of needing 1,500 GPM through each heat exchanger, I only need 1,000. That's a total of 2,000 gallons per minute system flow. So my left-hand system here is running the pumps at 100% speed and controlling with the flow control valves there. System on the right-hand side, I went into the control valve junctions. On the optional tab, I said fully open, no control. Fully open, no control, I'm going to have no loss. And the reason for that is because if I have my pumps operating on a variable speed drive, I don't need the control valves. So I'm ignoring them. On my pumps, for each of these, what I did was I went to the variable speed tab and I specified a flow set point, 667 gallons per minute. That's 2,000 divided by 3 pumps right there. The next thing I did was I set up my energy cost calculation. So I went to analysis, and then under cost calculation, I did pump energy only. And then for my cost settings, I'm assuming 10 cents per kilowatt hour. This is 12 hours a day, 365 days a year of off-peak operation. Once that was done, in order to get my cost report, I had to go into each pump on the cost tab, just include the cost for that object in the report. You could do this globally. So I selected all 6 pumps in the workspace and globally edited them to all include their costs in the report. So let's run this scenario here. When this scenario runs, it calculates all the results like it usually does. If we go to the pump summary tab, we can see that we are where our operation is. Let me click back on my pointer here real quick. And I want to make this text a bit larger. There we go. So let's look at something here. Percent of best efficiency point. When I'm using my flow control valves to control the flow rate, it's operating at 65% of the BEP. That's going to cause some major reliability issues on the pumps. You do not want to do that. If you incorporate a variable speed drive, look at this. If you drop the speed by about 34%, you can still be operating at 97% of your best efficiency point. So this is where you're going to experience the energy cost savings. So if I go to my cost report tab, you'll see the total costs of both individual systems. So with control valves, you're looking at $165,000 a year for each pump versus with a variable speed drive, $56,000 for each pump. Well, what are the total cost ramifications on that? I've got a spreadsheet for that I'm going to open up here real quick and just show you the total costs overall. As that's opening, I'll go ahead and drag it over. So here's my peak hours. As you can see, for my peak hour operation using control valves, it's $574,000 a year. With a variable speed drive, you get $558,000. So that is, $15,000 a year of savings. And again, this is a dinky little system. It's not real. Imagine if you did this for your own system that was real. Off-peak hour operation, this is significant. So here you're looking at almost $500,000 a year in energy costs using control valves versus $167,000. So you've got $326,000 in annual savings by switching to a variable speed drive. Much, much better operation. You've got some significant operating savings there. Total of $341,000 when you add the peak time and off-peak time together. But ultimately, your pumps are operating much more efficiently. 95% of their best efficiency points. You're going to be avoiding those issues. So that's how you do a very quick energy cost calculation of Fathom. It's not that hard. You just go in there and turn on your pump energy costs and go into each pump junction and say include this energy cost in the report, and bam, it'll figure out how much money you're going to be saving instantly. All right. Next example is how you can solve problems with AFT Fathom, goal seeking control module, and the extended time simulation modules. Again, the way that you turn on the add-on modules is when you're in Fathom, there's two ways. You can click on the button to the left of the status light, or you can go to the tools menu and then click on activate module. So I'm using the goal seeking control module and the extended time simulation module. And here's my system. Well, the capabilities, they greatly expand real system simulation, opens up a whole new world of creative modeling. So here's what we have going on. A very simple system where I've got a finite tank right here. If you use the XTS module, you can model a non-infinite reservoir. So you can model a full tank geometry, and you can put the tank heights. You can have them be open tanks or closed tanks. If they're open, you'll be notified if they overflow or not. And so I've got a finite tank up here, and so down in the bottom, I have an assigned flow junction, okay? So my assigned flow junction, that specifies a flow set point at that location. The way that Fathom does that is it changes the pressure at that junction in order to give you the flow rate that you want, okay? That's steady state. But when you turn on the extended time simulation module to do a transient simulation, what you can do is specify a transient flow profile over time. So this is actually how my flow rate changes at that location over a day period. This is your flow demand, okay? So over 24 hours, you have an increase in flow at a point in the day, and it drops off, and then you have another increase in flow. So that's how my flow rate is changing over time. Well, the next thing is I have a requirement where my liquid tank supply or my liquid tank height needs to be the same. I don't want it to drain. So the liquid height there needs to stay constant. The way that I'm going to do that is by using the goal seeking control module. I'm going to vary the pump speed in order to maintain a constant liquid height for my supply tank. I'm not going to run the model here. This is actually one of our standard examples built into Fathom. If you go to the help menu in Fathom and then under show examples, pick your desired units, it will bring up our examples help file, and you can find all of our tutorial examples here. Read them and they'll walk you through how to build the model of that particular system, and you'll learn a lot of useful features about the software. And so this example is the fixed head supply tank right here. This will walk you through that whole model building process, and it'll highlight what it does. So I just want to highlight the overall results. When I went through this, I noticed that my pressures were dropping below my vapor pressure at a certain time. So the blue line, that's the pressure at that assigned flow junction. So what you can see here is as the red line, which is your volumetric flow rate, this is your flow profile that you specified, as that flow demand increases, your pressure drops. And it drops below vapor pressure, which is right about here. You are cavitating at this time for several hours. And then you increase your pressure again because the flow drops again. And then later on in the day, you have another increase in flow rate, so you have another associated drop in pressure. You're cavitating again. Major problems. So they're not related to energy costs, but it just goes to show if you did a good flow analysis, it would uncover a operational problem in a very unintuitive place. So when you're dealing with AFT Fathom, you'll see cavitation can happen at high flow rates. So as that flow rate increases at that flow junction, your velocity increases, and that's where you cavitate. Fathom does not model transient cavitation. It simply identifies where it's happening. So your goal would be to figure out ways to eliminate the cavitation. So this is the advantage of having a good flow analysis. Okay, so now I'm going to shift gears and I'm going to go into some pump and system curve stuff, okay? And we're going to talk about what it means for pumps to complete hydraulically. Well, as I said before, if you've got pumps in parallel, especially if they're not the same, they're going to try to dominate each other, and one of them is going to end up providing a higher flow. This happens a lot if you do not have the same pumps, or if you have different piping for each of the parallel pumps. Each pump will shift to its own operating point that will impact each pump's individual efficiencies. Pumps with lower efficiencies lead to higher energy costs, but not only that, they operate further away from their best efficiency point. That's going to cause problems and going to lead to higher repair costs. And so again, that competition impacts your pump's reliability. So this is a graph of a pump curve that you could probably easily find with doing a Google search. And this identifies the problem areas on a pump curve. So this is the sweet spot where you want to operate. That is your design point. Your best efficiency point is right here where you have the highest efficiency. You want to try and be within 10 to 20% of that area. As you ride back on your curve, when your flow decreases, you have all these different problems that you start to encounter. High temperature rise, low flow cavitation, low bearing and seal life due to vibrations, reduced impeller life, suction recirculation, discharge recirculation. Those are all bad things that you want to avoid, and it happens when you're operating at flow rates less than your best efficiency point. When you get to be higher than your BEP, you also have issues with seals and then high flow cavitation. So definitely stuff that you want to avoid there. This is a useful curve that plots essentially the same pump curve with those problem areas, but it shows another curve. This is your reliability curve right here. And so what you want to be is within this area of flow. So you want to be within this flow range of your best efficiency point. That's your allowable. Best practice is to stay within this range right here. As you start to operate further out on this bell curve, your reliability dramatically decreases on both sides for low flows and high flows. So this just superimposes what your reliability of your pump looks like on top of its pump curve. And as you can see, when that flow drops, it drops very quickly, and it's going to decrease your mean time between failures. So that's a useful graph to conceptually keep in mind. This is another graph that shows vibration versus distance from the best efficiency point. So you have two curves. We've got a magenta curve and a blue curve. The magenta is for a fixed speed pump, always operating at 100% speed. And then the blue is a variable speed pump. So if you follow this, you can see how the flow rate changes for the pump all throughout the system here. And so that's your changing flow rate in the pink line. Well, if your best efficiency point is right here, when you operate further and further away from it, you can see how you have much increased levels of vibration. However, if you're using a variable speed drive, then you're able to control to these different flow rates, and you have a lot less vibrational issues. So that just is another graph that illustrates how it's useful to focus on the doing a VSD. Again, it's not just a VSD though. It's not going to fix all your problems. You got to look at see what's going on at a system level. So here we're going to start talking about pump and system curves. Pumps and systems need to overcome two fundamental aspects. They have to overcome friction, so that's your standard frictional losses in a pipe, and static head. Static head is your liquid elevation differences from your reservoirs. Or if you have pressurized tanks. If you have pressurized tanks, your liquid heights could be the same, but then your static head is going to be based upon the pressure differences in that case. Here's what I want to do really quick. I want to open up another Fathom model real fast. So give me just 1 second here. I want to illustrate what a system curve is. While that's opening, I'm going to go forward my presentation. What is a system curve? A system curve represents the pump head required to move your fluid through a system at various flow rates. So what it tells you is how much head you need on your pump in order to drive flow at various resistances. If you don't have any control features or control valves, your system curve and your pump curve will intersect at the operating point. So here's what this looks like. The blue curve is your pump curve, the red curve is your system curve. Where they intersect, that's your operating point right there. Okay, so again, the system curve represents what pump head that you need at each of these different flows. So you've got different flow rates, and as you have different flow rates, you've got resistances through your system. And as your flow rate increases, your system resistance increases. At each flow point, this system curve represents how much pressure or pump head you need in order to drive that specific flow through your system there. So that's what a system curve represents. Your total dynamic head is where your pump is operating at. That's made up of your two components. Your static head, again, that is your liquid surface elevation differences. And then you've got your frictional head component. So your frictional head plus your static head is your total dynamic head. Total dynamic head is what your pump curve is reading off. What are systems good for? They will help you demonstrate your pumping system behavior in a graphical manner. If you can determine a pump and system curve, it can help you identify effects or impacts by modifying the system. So let me give you an example now that my model is open here. Okay, so I have two scenarios. Right now I'm looking at the pump curve scenario. This is a very simple system. I've got a single continuous flow path. I've got a lot of frictional resistance due to a filter, a heat exchanger, which is not a real heat exchanger in this model. That heat exchanger represents simply a whole internal piping system of a plant, and I've just lumped all the losses into that one component as a resistance curve. And then I've got a valve, and then this is a really long pipe right here, and I've got some internal fittings and losses on there. Okay, and so I have a pump curve built into my pump property window, and in the enter curve data window here, I am going to turn on my preferred operating range. You'll see what that does. So when I run my pump, this is what the system was originally designed for. My design flow is 500 gallons per minute. Okay, so with this system being well designed for 500 gallons per minute, you can see that your my piping velocities are below 6 feet per second. That's what I wanted. And then if you look at the percent of the BEP, we're operating at 95% of the best efficiency point. So we're doing really good with our operation there. If we look at the applied standards, that's where our preferred operating range comes from. So I'm using the Hydraulic Institute standard for my preferred operating range, which has to keep my pump operating between 70 and 120% of the BEP. I then went to my graph results tab, and I have a pre-developed pump and system curve. So if I plot this right here, I've got several things on the graph. I've got my red curve, which is just my regular pump curve. The blue curve represents my system curve. So I've got my static head component, and then I have my friction component right here. Okay, that's the frictional component of the system. Now, what are these two blue dots? Well, that's my preferred operating range. So this is 70% of the BEP. This is 120% of the BEP. Where's my best efficiency point? Well, the yellow curve is my efficiency curve, so the BEP is going to be right about here. Okay, so if I drew a vertical line, that's my best efficiency point. Well, Here's my operating point. It's very close to that BEP, so it's really good. I want to make sure that this operating point does not go this direction or this direction past these X's right here, okay? So in this original design, everything is working exactly the way it should, and it's doing a phenomenal job. I have another scenario where I later had an expansion. So basically, I took this system right here and I duplicated it and I modified it slightly. So this is a whole individual portion of the system. So now, when I run my original pump with this new system, the flow rate is going to be different. So based upon my new flow rates here, if I go to my applied standards, this is my operating range there. I'm operating at 112% of the BEP. So I'm still not outside that window, but you can see your flow is higher, 595 gallons per minute. Well, here's what my pump and system curve looks like for that expanded system. Let me double click on that again. So here you go. As you can see here, you are operating still between these blue X's, but look, you're getting a little bit further away from that best efficiency point. Well, what I did was I took this data and I put it into a spreadsheet, not that spreadsheet, that's my other spreadsheet, and I actually plotted the system curves together. Let me open that up and show it to you. Okay. So what I did was in Fathom, I simply went to this button right here and I said copy the XY data and I pasted it right into Excel. So I've got my flow rate, this is my pump head curve, this is my system curve, and this is my efficiency curve. Okay, the orange dotted line right here is my initial system curve without the expansion. Okay, so that's this line right here. The yellow line, this is my system curve with an expansion. So as you can see here, when I added on my expansion of the system, I don't have a unique system curve. It's not the same system curve anymore. So my system curve moves, okay? This red line right here, that's my best efficiency point. Well, my pump curve is going to keep operating on the same curve, however. So what happened in this situation is when I put on that expansion, my system curve moved. So I have a new system curve and my flow rate moved as well. So I'm operating at a higher flow at this location now. So you can plot your system curves together like this in Excel, and you can see how making these changes will operate your system. And as you get further and further away from your best efficiency point, that's not a good thing. Okay, well, I've got 2 minutes left. And so that's not enough time to cover the rest of these slides here, but there's a lot of good information about pump and system curves. If you go through this in my slides here, you'll learn a lot of aspects about how you can use pump and system curves effectively in order to better analyze your system. And essentially, here's something that is interesting is, people will put multiple pumps in parallel to try and get more flow. Okay, so if you remember this from college, this is theoretical where you put more pumps in parallel, you should get higher flow rate. Well, that doesn't happen. Okay, it depends on what your system curve looks like. If you have a steep system curve like this where you have a lot of frictional resistance, you can clearly see how adding more pumps in parallel does not generate that much more flow. So this is an excellent way to show people that just adding more pumps in parallel, that's not going to do it. It's going to make your system run worse. You're going to have more problems, more efficiency issues, and it's not going to operate well. So what you need to do is if you have a lot of friction in your system here, you got to change your system. Maybe you have to go in and do a retrofit. Maybe you need to do, some larger pipes larger pipe diameters throughout your system, because if you want to get more flows, your velocities are going to go up. So for higher velocities, you got higher pressure losses, and that's going to cause problems. So understanding this pump and system curve interaction is key, and it'll help you design systems better from the get-go, and it'll help you maintain and operate existing systems a lot more efficiently as well. And it'll really do a good job at helping you increase the overall profitability of this system. So that's what I had for today. And I tell you, I love doing these webinars, but an hour is never enough. So if any of you have any questions on this pump and system curve concepts, don't hesitate to give me a call, okay? Give me a call. Email me at benkeiser@aft.com. I'll be happy to go over these pump and system curve concepts with you if you have any questions on them. That way you can understand that stuff a lot better. My email is benkeiser@aft.com, and you can contact us at our phone number. Technical support you can get through support@aft.com. If you have questions about our individual products, you can email us at sales@aft.com as well. Thank you all very much for your time today, and the recording will be sent out. For those that listen live, you should have immediate access to my presentation right now as a PDF. For those of you that are listening to the recording later, email me and I'll send you my presentation. Take care, everyone, and have a wonderful day.